ready to start presenting, please.
Okay. Hello everyone, this is Peng Zhang from Team China, and today I will bring you a report on question number 15, pancake rotation. Here is the content of my report. For the introduction section, we'll first do a brief question review. Place a few balls in a round container. If you move the container around a vertical axis, the balls can move co-directionally with the movement of the container, or they can move in the opposite direction. Explain this phenomenon and investigate how the direction of movement depends on relevant parameters. From the question, we can roughly derive three categories of independent variables: properties of the balls, properties of the container, and that of the dynamic system. As for the dependent variables that need to be investigated in our report, we have the overall direction of rotation, whose definition we will clarify later, and the critical number of the balls in order to change phase, which means for the direction to change. Well, here is an explanation about what we call the direction of rotation. Here we define omega BC, which denotes the average angular velocity of balls relative to the center of the container over a long enough period of time. The direction is defined by whether the sign of omega BC is the same as the angular velocity of the container. Next is our preliminary experiment. Here are two videos showing different rotation directions observed in our preliminary. Here are some of our findings. Generally, when n increases, omega BC decreases from positive to negative and eventually increases back to a certain degree. When other conditions are controlled, it increases along with omega c. N critical increases at a larger radius of the container but decreases at a larger radius of the balls. Here, I present you an overview of all the variables. For the independent variables, we have the coefficients of friction between the ball and the container and in between balls, the radius, mass, and moment of inertia of the balls, and the radius of the container, the angular velocity of the container, the amplitude of rotation A, the linear velocity of the system, and most importantly, the number of balls. And for dependent variables, we have the average angular velocity of the balls, and certainly the critical number of balls to affect a change in the rotation direction. Now we will step into our theoretical model. Here is the structure of our theory. First, we will try to make a qualitative explanation of the phenomenon. One perspective is energy balance. The co-directional movement of the swarm of balls along with the container requires the kinetic energy provided through collision and friction with the ball. With the wall. When there are more balls, each one gets a smaller share of the total energy, so that the movement of individual balls in the lab frame is gradually reduced, until they cannot follow the rotation in the frame of the container, ending up in counter-rotation. And what can be analogized to geometric frustration, which is a concept in condensed matter physics, preventing single balls from rolling and spinning freely. The cluster of balls rolls like a rigid body on the container wall with a no-slip boundary condition, eventually leading to what we call counter-rotation. Now we can take a look at our fundamental model. We want to start from particular collisions that take place in the system during the movement and study its holistic behavior after relaxation. Here is how we would describe the dynamic state of a ball after each step. Each variable that describes its state of motion is iterated over and over again, as shown on the slides. Here is how we model the elastic collisions between balls. We would first want to resolve the initial velocity in the normal direction and the tangential direction. Then, since the normal velocity change is easy to obtain, we now express the change in tangential velocities. This change is determined with a series of derivations associated with impulse, as you can see on my slide. And finally, the changes of velocities of both balls can be brought back into the original xy coordinate system, enabling a next iteration. The ball-wall collision is calculated by considering the wall as an extremely big ball. This calculation is very similar to the ball-ball collision, so we will not further elaborate here. One thing that must be noted is that the angular velocity has two components associated with the collision, which are calculated separately. Although they are not directly visible in the movement of the balls we discussed, they are necessary for the calculation of velocity and acceleration after each step. Now, we did some simulation based on the previous derivation in order to obtain the results. Now we know that console is time inefficient due to its 3D simulation by mesh, and it would take forever for us to simulate the phenomenon with console. Therefore, we used a simpler substitution, which is a two-dimensional simulation built with Python. We will be able to see details about simulation in the appendix if it is of interest in our discussion later. Now that we obtained the results from the simulation, we will next state our predictions. Through the simulation, we obtained the numerical relationship between 7 independent variables in our critical number for the counter rotation, and more fundamentally, their relationships with omega BC. The results are shown here, and here on this page. As we will discuss and compare these results later in the experimental part, I will first present to you some analytical results we obtained under large N conditions where counter rotation occurs, which is also the phenomenon that gave the problem its name. Think about it, when you hold a pan and cook a pancake, the pancake could counter rotate just like our balls do when N is large. Now we can look back at our balls, and when we do so, we can easily see that they move in a similar pattern. The swarm of balls rotate together like a rigid body, and the track of one single ball looks just like a cycloid. Now, we can calculate the angular velocity of a cycloid and translate it into our system. What must be paid attention to is that there is a variation in the density of the pancake when the number of the balls change. So the result of this solution is an interval, as shown on the right, rather than a certain value. Back to our model. Here is the question again. And we are confident that it is fully answered through our research. We have already discussed energy balance, and the analysis we just discussed is completely based on the perspective of geometric illustration. On the right is our solutions through calculation, which we will next discuss in our experiment. Next is our experiments. Here is the content of our experiment, the list of variables we experimented on, and here is an overview of the experiments again. For the setup of our experiment, here is an animation of our equipment works. And this is a detailed explanation of the setup. The camera appears in the frame of the container right above the container. Step motors are in opposite angular velocity in order to keep the plate at a constant direction. One motor directly under the dish and the other under the movable support. We also did experiments to make sure that the container translates without rotating. As you can see that the red bar on the right is always at a constant direction. Now, we have different Petri dishes characterized by different sizes and textures. We also have balls with different sizes, textures, and masses. Note that although we only displayed 2 on the slides, each parameter is changed at least 4 times. After we recorded the motion of the balls, we used the tracker to collect and analyze the data. One important thing is that when the radius of the ball is not significantly smaller than the container, the addition of one ball at the threshold may drag the whole swarm into counter rotation. And in such case, we recorded the N critical before counter rotation instead of after. First is our most important comparison. Just as our theory predicted omega BC decreased and then increased back to a limited degree when N increases. N critical is at the turning point. After the turning point, we can also see that this relationship agrees well with our analytical prediction where cycloid under the large N approximation. Here is the tendency of omega BC and N critical's change to omega C. There is a positive correlation between them. The correlation is also positive in the experiment on rotation amplitude A. For the friction of coefficient between a ball and the container, the correlation is negative, which is also true for a coefficient of friction between the balls themselves. I would like to clarify here that in the experimental mass, hollow and solid balls of the same material are used to change the mass while keeping the ball radius and coefficient of friction constant. This method would indeed change the moment of inertia of the balls. However, both variables play similar roles in increasing the energy required to alter the ball's motion state, either of translation or rotation. Therefore, from both perspectives, the two variables increasing, both likely to make the balls move together like a pancake. The two variables are changed together also in simulation, and the results still fit very well, validating this approach. Incredible has a negative correlation to the radius of the balls, and it has a positive one to that of the container. Here is a summary of our experimental results. All the results match with our theory perfectly well, as you can see in the form on the left. Now, we can enter the conclusion section. This is a brief overview of all of our results, including the two explanations that we already discussed multiple times, the perspective of energy balance, where the energy required for balls to rotate must be offered by collision and friction of the wall, and that when the number of balls increase, each ball gets a smaller share, and the explanation of geometric frustration, where when there are too many balls, they will form a special structure that increases the total friction, and so that they move together like a pancake, which is also what the explanation that we base our analysis on. Back to the question, it asks that the explanation and investigations must be done in the phenomenon, and we believe that through our report, we have successfully fulfilled the quest. Here is an error analysis. Systematic errors arise due to factors like energy loss from fluid resistance and energy loss through sound during collisions. On the other hand, random errors are caused by unpredictable occurrences, such as the random approaching of ball enter resulting in abnormally high angular velocities or the packing of balls.
Thank you. Thank you. We don't have to see the appendix. That's your time up. So we now have 2 minutes of clarifying questions from the opponent, please.
Hi. First of all, is the frictional force or the centrifugal force dominating this phenomenon?
Excuse me, this friction force or the?
Centrifugal force.
We think it is a friction.
Okay. Do you analyze the self-rotation in your experiment?
What do you mean self-rotation?
Like the self-rotation of the balls.
No, we did not.
Then do you consider it in your simulation?
Yes, we did. We used the angular velocities to.
So it's as a 2-dimension or 3-dimension model.
You mean the simulation?
Yes, simulation.
The simulation is 2-dimensional.
Okay, thank you. Will it have a boundary condition that counter rotation never happens?
A boundary condition that counter rotation never happens?
Yes. Even with high amounts of ball.
No, there is no such analysis.
Okay, so did the boundary condition exist?
Excuse me?
Did the boundary condition exist?
We think that if you we think that it might exist.
Okay, thank you. Will it have a constant ratio if you change different balls or different size of the balls? Will it have a constant ratio to counter rotate?
What happens to the?
Sorry, I will skip to the next one. Do you think the initial distribution will affect the phenomenon?
No, we gave the system enough time to relax.
Okay, and do you have analysis on collision to show it's elastic?
We did. Our whole.
In the experiment.
Okay, thank you. You have 5 minutes for the preparation of your opposition speech. Thank you. And please, at 4 minutes, start presenting and then sharing your screen.
那个会影响往上一上。
就是我回去给你。
不然你等下报告的时候你戴耳机，这样。
我戴耳机，大家怎么听到？
哦，好吧。
为什么会有回音啊？
然后开麦克风的时候，
这个你们听见？
那你们都戴耳机，然后不要放上来，这里在这里才会录到。
No analysis of the angular velocity change by different amounts of
angular velocity change of different
amounts of。
你刚才重点要说 fail to find the boundary condition。
对，然后还有 simulation 里面没有 self rotation， 还有boundary， 然后
这个它全部都没有，但是你要把它讲，就跟 Pancake 一样。
你就说没有可以，它只有那个 critical number。也就是说 critical number 是在什么时间就好？
不是
stone 挂 critical synchronous 删掉，然后 start 删掉。
对，那个方法。
要把它打 into dimensional simulation 吗？
Yeah。
我在戴耳机。你自己的那个。好。这会放哪？可以放。
我问的还好吗？
谢谢。
声音有不清楚。
很好。然后你刚刚自己开你电脑的。
自己开我电脑。
我去了。我拖你上去。
3分10秒。
还有个 tangential velocity， 应该是 velocity。
不用了。
我如果你写这么多，你常会有太多，你不写是吧？
对啊，他们就没有 self rotation。这种是。verification 啊，应该是他可能。
然后 friction from the bottom consider。
啊，什么？太讨厌了。
Perfect. You're ready. Post.
Hello everyone, I'm Woodry and local competitor. I'm the opponent from Team Taiwan, Vincent, opposing partner number 15, Pancake rotation. First of all, I believe the key point of this problem is finding the critical points to counter rotation and how did the rotation change with different amounts of the balls. Then this is the overview of the report. First of all, I believe we can organize the phenomenon shown in the report into 3 stages. About rotation, which move co-directionally, and stall, which same as the rotating velocity of container, and counter rotation, which is the main phenomenon we are going to investigate. So in their report, I believe a definition for transition zone is not clear enough since there is a stage which is stall, and they didn't have a clear definition of the counter rotation. And also they failed to find and explain the boundary condition. Then for the simulation that's a modeling using Python, they calculate tangential velocity and consider elastic collision between ball and also balls and walls. However, they didn't have a verification on elastic friction. And also, they mentioned in the equation that the frictional force causing the balls to spin, and with higher density, the balls will not spin, and then it will counter-rotate. However, according to this explanation, they didn't consider it's a simulation. So I believe the simulation is incorrect, and it's need to consider the self-rotation. That's didn't consider in their code. Then for the experimental part, that first of all they change a particle cluster and change properties of the balls and also properties of the container, which will change the particle cluster density. And I believe there's a constant ratio. And however, they didn't mention the interparticle friction, and they didn't find the exact critical points, and change with different amounts of the ball. Then for the second part of the experiment, they change the radius of container and also rotational speed. However, I believe this part they can normalize the phenomenon to see if it has a constant ratio of the density of the balls with different parameters. And they didn't have an analysis of the angular velocity change of different amounts of the balls. And then in the discussing points later, first of all, I'm going to discuss the whole physics picture of this phenomenon, which is the role of forces between the balls and the wall, and also between the balls and the ball for the balls to counter-rotate, and why will these forces and the friction cause the ball to counter-rotate. Then for the second part, I'm going to discuss the centrifugal force pushes the ball, and how will the distribution related to the counter-rotation, and how will the angular velocity be like as different parts of the cluster, since we know that there's a inner part and outer part, and also the more loose part and more dense part. And I'm going to discuss the angular velocity difference as different parts. Then I'm going to discuss is there a constant critical density of the balls to counter-rotate, and if the friction is really small, since the reporter believes friction is the main forces that cause counter-rotate, I would like to discuss the boundary condition that will not exist counter-rotation, and also some deviation analysis of the experiments later. And this is the end of the report. Thank you.
Thank you, Mr. Hoplock. So now we have 10 minutes for
Okay. First of all, since you believe friction is the main reason for the phenomenon, can you briefly explain how well